Thank you very much for the generous introduction and for inviting me to give this talk. So as far as the stats talk goes, to be honest, this is going to be there's less kind of mathematical detail here than a typical statistics talk, but I chose to talk about this because I think I still want to kind of expose statisticians to this topic. I think it's an incredibly important area for statisticians to get involved in my biased opinion, of course. And I will give you lots of examples throughout the talk of statistical problems that come up along the way. So I think it's also ripe with opportunities for statisticians to help. So let's get started. So let me tell you about Delphi as a group before we dive into some of Delphi's work. So Delphi is a group that's based out of Carnegie Mellon. It was formed in 2012. Another faculty at Carnegie Mellon, whose name is Roni Rosenfeld, who's the other principal investigator of the group, and myself, started this group with just 2 students in 2012 to develop the theory and practice of epidemic forecasting. And the main thing we did between 2012 and basically right before the pandemic was to build models, and not just models, but actually operational systems, which ran every week to track and forecast seasonal influenza. And the CDC, starting in 2013, began these influenza forecasting challenges, which are still going on today, by the way. This is the first year that we revisited them in some way that was not dominated by COVID. So the flu this year is very bad, and it's actually quite early. And so the big focus right now in the CDC forecasting community is on influenza forecasting. So we've returned to this this endeavor this year for the first time since pre-pandemic. And we were among the most accurate forecasters in most of the years between 2012 and pre-pandemic. And we started to develop a bit of our name for ourselves in the community. And we were also the only group in the community, not the only group, we were one of the only groups in the community who early on started to use statistical models for forecasting. At this point now, there's quite a number of groups that do, but early on, it was quite a small community, and most approaches were based on kind of mechanistic models for disease transmission. And we, not being epidemiologists or not having a background in the mechanism of disease transmission, we just started to build statistical time series models that were based off of historical trends of influenza in order to forecast influenza. And this proved to be pretty useful. We were awarded the CDC National Center of Excellence for flu forecasting. It's now flu and COVID forecasting, informally speaking, in 2019. And one thing that I like to kind of reflect on is that in applying for this National Center of Excellence, it's basically a grant that we were awarded. Applying for this grant, we had to write about what we would do in a pandemic. So there was kind of 5 different sections of the grant that we had to address certain topics. And one of the topics was the CDC was concerned about an influenza pandemic that might emerge, because these happen about every 30 years in the US, more or less. And we didn't really know what to write there. We had no experience in pandemic tracking or pandemic modeling. It was very far from the kind of work that we'd been doing for the previous 7 or 8 years. So that was by far the weakest part of our proposal, in my opinion, because it was, just ideas. And then we were awarded this Center of Excellence in about September of 2019. And then only a few months later did a pandemic emerge that was actually coronavirus pandemic, of course. So it's kind of funny that we've been thinking about that in the months preceding, and we pivoted completely to focus on tracking and forecasting COVID, as did basically everybody in the community and also in the CDC who was working on flu forecasting before that. And our group went from about 6 or 7 people at end of 2019 to now has about between 30 and 35 people. I say about because we have many volunteers that kind of would come in for projects. And so at any one point in time, it's not really exactly clear how big the group is. And at our peak in the pandemic, we had well over 60 and probably even over 80 at one point. So the thing that we've been working on primarily for the pandemic period was actually not forecasting, even though that's probably the thing that people would most obviously associate with a statistician's role in epidemics. But it's actually been on the surveillance and tracking side. And so that's what I'm going to talk to you about today. And I really think that this is an extremely important area, and it's definitely overshadowed by forecasting. But this has been our focus for the majority of the pandemic. And I should say, actually, let me do that right now. I should have done this initially. Let me stop sharing, and let me give you a link to my slides, because they're publicly accessible so that you can just follow along with me if you'd like. Just going to grab the link, share. Anyone with the link, just updating the sharing settings. Okay, here are the slides. You're welcome to follow along, or of course, return to them at some later point if you'd like more details on something I didn't cover. Go back now. Okay. So this is a kind of schematic of COVIDcast. Oh yeah, there's a question. Does somebody want to ask a question? No? Okay, so this is a schematic of basically of what COVIDcast is about. This was the name of the project this is the name we gave to the pandemic efforts, basically. It's more than one project. It's kind of many things folded in one. I'm just going to kind of quickly go through it to give you a sense of the kind of thing that we were working on over the pandemic, and then this dovetails into the stuff that we're working on now. So at the bottom of this picture are the graphics of a bunch of companies, and we early on in the pandemic established relationships with various partners in tech and healthcare, and some of these relationships actually existed prior to the pandemic. So we've been working with Optum, for example, we've been talking with them for some number of years prior to the pandemic, and same with Quidel as an example. But others emerged, from the pandemic, early on in the pandemic, and we basically, unique to each of these partners, we have a certain mechanism for getting data from them, and every day we have code that runs that creates signals from these unique data sources that reflect pandemic activity that aren't traditionally, recorded in public health. And we create these signals on an automated fashion, like overnight, for example. And then we populate a large repository with these signals that reflect pandemic activity across primarily the United States. And this repository, it not only has unique kind of auxiliary signals that exist outside of traditional public health, but it also includes all common public health reporting. Like, for example, confirmed cases, hospitalizations, and deaths. And critically, this is a very important point that I think will play a role in many of the parts of my talk. We record all data revisions, even when the data source does not. One level up from that, we have an API which allows anybody to access this repository, the COVIDcast repository. And we have R and Python packages for data access, for plotting, and for processing data. We have dashboards that we've built for non-technical end users, for example, primarily, but also for anybody, even if you like to code, sometimes it's useful to have a dashboard. There's one that's dedicated to this survey that we ran in collaboration with Facebook called CDIS, the COVID Trends and Impact Survey, because that's a very rich source of data. And then there's one that's kind of general that displays signals across COVIDcast. And then on the top right of this picture, there's some packages that we have built for model development, for forecasting, hotspot detection, nowcasting, and model evaluation that we use ourselves in some of our operational modeling endeavors. And all of the stuff in the top right I want to maybe emphasize is actually we have kind of next generation versions of them that I'll allude to a bit later. These still exist, they're still functional, but everything here is kind of slowly being replaced by more general software packages that I think are, of course, sometimes it helps to revise things. We think we can do it better than what we did here, so that's what we're doing now. And also, when you have the slides, all of these should be links. So if you were to click on, for example, any of these, then it'll take you through to more information. Just as an interlude, because this is not primarily the focus of my talk, but I think it is worth describing it in some detail. I wanted to talk about the COVID Trends and Impact Survey. So this is something that is done. It was actually shut down in June of 2022, but it ran continuously from April 2020 to June 2022. And we started this survey in collaboration with Facebook and also various other partners in academia and public health. And it's called the COVID Trends and Impact Survey. Early on, you may have heard it called something else, or actually not even early on. For the first year and a half, it didn't really have a name. We just called it the COVID Symptom Survey. But it's now called the COVID Trends and Impact Survey to better kind of reflect what it's about. So it's a survey that Facebook advertised to a random subset of users that we ran, Carnegie Mellon's Delphi group ran basically outside of Facebook. So they would help recruit respondents to take our survey, which was implemented completely outside of Facebook on our own side through Qualtrics. So Facebook never had access to any survey information whatsoever. They just served very generously as a recruitment platform. And in total, over the life of the survey, there were about 30 million total respondents in the US and over 35,000 per day. It was 50,000 per day for most of the life of the survey, and then towards the end, the participation started waning due to pandemic fatigue, and we decided to shut down the survey at some point due to the fact that we thought that it had lived its course. So the topics were wide-ranging from symptoms. This was the initial interest to have people self-reporting their symptoms in real time. But then it was much broader than kind of surveillance type signals, like, for example, symptom and testing, but aspects of mental health, aspects of regular social contacts, occupation, demographics, behavior, hesitation about vaccination, risk mitigation, all sorts of things basically got included in the survey, and it had 12 survey waves. So it was updated 12 times throughout its life in response to what we thought the biggest needs were at the time. And this was done in collaboration with public health experts, and, for example, at the CDC and at the White House as well. So there was a lot of interest, for example, in January 2021 about reasons for vaccine hesitancy. So we made many revisions around that time. Not many, we made some key revisions around that time to the survey in order to try to address that. So the reason I'm describing this in such detail is that I'm trying to get you interested in maybe using the survey to shed in, to develop new insights retrospectively about how the pandemic affected people in the US. But I think it's still a very open and ripe topic for research. So you can get the microdata, which means the individual survey responses, all 30 million individual responses, through a data use agreement. And this link will take you to it. The data use agreement, it's free. The data use agreement basically limits what you can do with the microdata. So for privacy reasons, obviously, you can't publish an individual survey response online or in a paper, right? You can publish aggregates, and the DUA basically circumscribes types of aggregates that you can compute and publish. And these aggregates, some of them are openly available in our API, and we have some contingency tables up online as well. That now these are completely freely accessible without a DUA, these aggregates. And I should mention there's a global version of the survey that was run by the University of Maryland that was developed and carried out in parallel basically to the US-based survey that Delphi ran, and that reached over 100 countries. And I think, if I remember properly, it had over 150 million respondents internationally. So these are large, very large surveys with lots of data. And this is just an example of some research that's ongoing. It's carried out by Delphi group member Alex Reinhardt, who's a faculty in the statistics department at Carnegie Mellon. And Alex, for most of the life of the survey, was kind of the lead in the survey in terms of revisions and development and so on. And this is something that Alex is doing with some of his students and collaborators. They're kind of looking back at vaccine hesitancy and how it unfolded over time, and vaccine acceptance, and broken down by reasons and broken down by various demographics like age and race, for example, to try to get some sense of as to whether, for example, vaccination campaigns were successful. Okay, so that's that was my interlude. Let me return to kind of the main thread. So what does Delphi do as a group? I'll tell you, give you a high level after kind of weaving in and out of some details. In a nutshell, Delphi creates or maintains pipelines that take data from unique data streams mostly that reflect epidemic activity. And some of these data streams come from medical insurance claims, medical device data, app-based mobility data, search queries, and online surveys. We also maintain pipelines to traditional public health reporting streams. So this is like mandatory reporting on notifiable diseases. And from these pipelines, we derive informative signals. So this is where the statistics comes in to try to figure out what we can extract from these data streams, how we can best extract it, account for, noise, bias, missingness, and so on and so forth. I'll tell you more about that the rest of the talk. And we maintain a repository with public API access. Stuff I won't talk about today, basically at all, is that we run operational nowcasting and forecasting systems that use this data and traditional public health data for flu and COVID, nowcasting and forecasting. We develop open source software packages that support the same tasks so that others can benefit from some of the infrastructure that we've developed and the models that we've developed. And of course, being academics, we try to find time. It's not always easy to do, when you're doing operational work. We try to find time to do research in the space of computational methods in these and related areas. And if you have the slides, here's some links and pointers to various things, that the group has done that will give you more information. And I alluded to the fact that we have some kind of next generation R packages that are in development for example, the epidemic processing and prediction tasks, and that's linked here on the bottom right in case you're curious. Okay, and I saw John Chambers on the call. I'll also just point out that we wrote a paper for an issue on statistical science that John helped organize with Chiara Sabati. That is also linked here. There's a special issue in statistical science on COVID-19. Okay, so the purpose of this talk is not to describe all of this. It's really just to describe the Epidata part of Delphi's work, which I think is probably one of our most central projects, and the associated opportunities and challenges that are presented with it.
Ryan, a quick question from the audience.
Yes, I don't have a way of saying that, but maybe you can tell me.
So can the GitHub repo be linked?
The GitHub repos?
Yeah.
Yeah, they're all linked in the previous. They're all linked here. So, for example, Epidata's GitHub repo is here. This is the repo that actually has the code that runs the API. So this is mostly like a development repo for us. Back now. Sorry about that. The links to the GitHub repo. I'm not sure what you heard me say, but they're on this page. And this is the link to the Delphi GitHuborg, which has all the repositories, and these are links to kind of specific repositories. So for example, well, these are both GitHubs down here to different packages. This is a GitHub repo for everything to do with COVIDcast, and this is a GitHub repo for the backend for the API itself. Okay, so let me tell you about Epidata. That's going to be the focus of the rest of the talk. And the way that I like to start describing Epidata is to describe the goal the goals that we're trying to achieve in building this. And this is, there are quite a number of goals here that I think are achievable and are, important goals for surveillance in terms of things that it's currently lacking. So the first goal is to try to make epidemic surveillance in the US. Everything here is about surveillance in the US at the moment. That's where our focus is. There's no reason why this couldn't be done internationally. I just think that it's not possible for us to do at the moment given our bandwidth. The goal is to make surveillance first more nimble and flexible. So we would want, let's say as citizens of the United States, for new pathogens or syndromes to be tracked basically in a matter of days or even hours after they become, of concern, not weeks or months. And this isn't really possible with traditional public health reporting. So to give you a sense, the universal compliance from hospitals in the United States in terms of reporting COVID admissions to the HHS, which is the Department of Health and Human Services, which was the agency collecting hospitalization data in the federal government, the compliance that was near universal from hospitals reporting wasn't achieved until December of 2020. So that was something like 7 or 8 months into the pandemic. And before that, we didn't have at least publicly available, comprehensive hospitalization data. It's a very long time for this to happen. Cases and deaths were around much earlier, but still that was a huge effort to set those up, which is a later point. Okay, we'd like surveillance to be more complete. We don't want to somehow limit our views to, only a few aspects of pandemic activity, like cases and deaths, which are the top line numbers, right, in terms of pandemic tracking. And then hospitalizations got added, like I said, almost like 8 months later. We would like to view data across all rungs of the severity pyramid, and I'll give you a visualization of what that means in a few slides. And critically, we'd like to be able to access these data signals with adequate revision records, because data gets revised very frequently in public health, and it can be very problematic to ignore those revisions. We like, and this is something that I think hopefully everybody in the call can understand and appreciate as, computational statisticians and data scientists. We'd like data to be standardized, in the sense that if you want to take data from one source and from another source in order to kind of perform some kind of either operational modeling task or research task, we don't want to spend time on data wrangling. That is something that is kind of notoriously time consuming and error prone. And we'd like, as best as possible, for data formats to be standardized so that time gets spent on the actual analysis, not on the wrangling. We like situation awareness to rely not just on one data stream, right? So if one data stream is all we have to understand, let's say, infections for some disease in some part of the country, we don't want our situational awareness to go completely black if that signal drops out. So we'd like some kind of robustness in the system which relies on information across many signals in order to infer what's happening. We'd like, of course, these types of inferences in terms of situational awarenesses to be as close to real time as possible. We don't want latency, we don't want signals to reflect things that happened in the past. And in fact, something that's not super well known, I'd say, or even really discussed very much, is that case reporting and death reporting they're really snapshots into the past. They're not real time. So when a case gets reported, the test that was performed corresponding to that case could have been anywhere between 1 and 40 days old. And the median for much of the pandemic was about 6 for the lag between the test date and the report date. But it has had quite a big right tail, so it could be much larger than that. And then several more goals. We'd like, surveillance to be less burdensome on public health itself. So public health officials, especially in a pandemic or in a situation where some new pathogen has emerged, they obviously have to spend time dealing with that at a local level, or whatever level, could be a state or federal level as well. We don't want the same people who are, focused on managing the pandemic or some pathogen of concern to also be responsible for reporting, so that we have some source of data to reflect what's happening, right? That's just a tremendous burden to place on top of basically an already full-time job. And the idea is that maybe there can be more automated surveillance that comes from outside sources that lessens the burden on not just public health, but also healthcare. And this point G is very, it's kind of very obvious. We want data to be as detailed as possible, geographically, temporally, demographically. We don't want to, we don't want to have only coarse views at our disposal. And that's often what happens with kind of traditional public health reporting. And the last 2 points here, I'm going to kind of skip over. These are more technological points, but I'll just summarize them in one sentence. We want any system for surveillance to be kind of self-correcting. If something goes wrong, we don't want humans to have to figure that out. We want the system itself to raise a flag and to say, well, something's missing, something seems anomalous, something seems to be emerging, and to draw human attention to it when needed, rather than rely entirely on humans to monitor the system. So these are a lot of goals, a lot of desiderata. I'll just repeat them again. We want surveillance to be more nimble and flexible, more complete, more standardized, more robust, more real-time, less burdensome, more detailed, and kind of self-correcting. So what could possibly achieve all of this? And of course, you already know the answer because that's what my talk is about. It's Epidata. I wouldn't say that Epidata is, kind of completely across the board achieving all of this right now. It is already achieving some number of these things right now to some degree, but I think it's completely capable of achieving all of these things once kind of seen through to what we consider, at least, let's say, the first finish line. There's not just one finish line, but the first finish line would be to achieve all of these across the board. And it's not just Epidata. I want to maybe make the point that it's not like we're the only people who are capable of achieving something like this, Delphi as a group or this particular system. I think this is also achievable with a variety of other systems. But the key is that these systems have to rely on data outside of traditional public health reporting in order to pull this off. And that's what we're doing. And so let me explain to you at like a bigger level what Epidata is, because I haven't really described it yet. I've just told you what I think it is trying to accomplish, and I've mentioned COVIDcast. So I'll tell you now where all this fits in. Epidata is a collection of repositories of real-time epidemic signals. So there's not one repository in Epidata, there's many. At this point, there's probably over 15. And we created this in 2015. And historically, we would create one repository per data source. So, for example, for some CDC data that has a network of hospitals and outpatient centers reporting on flu, this is a network called ILINet, Influenza-like Illness Network. For that data source, which is publicly available, we created a repository so that we would kind of have up-to-date API access to FluView just with queries and all revisions and so on and so forth. For the next data set of interest, maybe it was a data set on dengue fever, we had another repository, and so on and so forth. And so that was what we did for most of the years after 2015. For COVID, we actually kind of, mostly because it felt like a wartime effort and we were moving so fast, we combined many data sources into one big repository. So we kind of broke from the tradition. And COVIDcast is by far the biggest repository in Epidata, and it has many data sources in one. And to give you a sense of its scale, at this point, it's accumulated over 4.5 billion records, and we add about 3 million new records per day to COVIDcast. And we receive between 100,000 and 1 million API queries per day. So it's a big scale. It was originally developed, all of Epidata was originally developed to support the research and modeling community, of which I think that's kind of, the core identity of the group came from that community. But now we're working to make Epidata a key part of operational public health. So we want to professionalize it, and we want to kind of embed it into the workflow of public health outside of research. So here's the severity pyramid that I mentioned a few slides ago. This is what it looks like for COVID and for COVIDcast. So this is something that I think is a nice visualization of levels of burden, basically, for that a pathogen would present, everywhere from deaths at the very top to relevant population level behaviors at the very bottom and stuff in between. And the way to think about this, at least this is the way I think about it, is that to understand one rung on the severity pyramid, you typically think that it would be helpful to understand the rungs below it. There's this natural hierarchy to it. So in order to predict deaths, or for example, understand deaths retrospectively, we would want to be able to have access to critical hospitalizations like ICU admissions and just regular inpatient admissions. And that would be important. in order to understand hospitalizations, we probably also want to understand outpatient visits and, which cases are being reported and so on. So this is why I think kind of completeness is so important in epidemic tracking, is for that reason, because it helps, basically having completeness helps develop an understanding of the spread of a disease across these levels. And here on the right-hand side, I've written data sources in COVIDcast that reflect basically each rung, and they're color-coded by data sources that Delphi helped create, or that were kind of exist uniquely to Delphi's efforts. They're now publicly available, and ones in blue that we basically just mirror in the API so that we can have unified access to them. So now I'm going to jump into, I think, is the most interesting part of the talk, at least, maybe the most statistically oriented in terms of examples coming up. And I'm going to talk about a bunch of opportunities and challenges that are associated with auxiliary surveillance. And looks like I have about 15 minutes left. Is that right, Dihua?
I think you can go a little bit longer because we start late, 7 minutes late. We have a small interruption in the between. So I think you have 20-ish, yeah. That's
great. Okay. So I think I can probably get to all the examples then. So let's look at the first opportunity that I think auxiliary surveillance presents, which is to triangulate public health reports with auxiliary signals. So this is an example from the summer of 2020, the summer wave of 2020 of COVID in the South. This is actually Bexar County in Texas. This is the county that contains San Antonio. And these are the case reports over time. And so you can see somewhere in late July, we see a huge spike in case reporting. Okay, and this is from the county health department. And we could be sitting here at this dotted line, right, at this point in time. And we could be a concerned citizen, we could be a local business owner, we could be a school administrator. We could be trying to figure out, is this spike real, right? Should I be concerned about this wave? And in fact, I mean, at this point, it maybe was not so clear, but in hindsight, now we know that there are just many, many instances of this in case reporting, where there have been numerous times where spikes have appeared or drops have appeared that are not actually really affiliated with genuine COVID activity, but are basically artifacts of reporting. And this has happened so many times, it's hard to describe to you how frequently it happens, but it's just really happens very frequently. In this particular instance, I used to have a news article that was linked in this slide. I think I forgot. For some reason, I removed the link. You can read a news article that basically figured out that this was due to an audit that was run on the county that revealed thousands of cases that hadn't been reported, that just got basically reported over the course of a week. So this wasn't thousands of new cases that actually emerged that week. These were old cases that just somehow for whatever reason, logistically, or maybe it was just that they didn't meet the case definition at the time, and then they met the case definition now, or whatever it was, they got reported over the course of a week. So obviously this is tremendously difficult to deal with, both informally as a person trying to gain situational awareness, and also as a modeler trying to predict COVID, right? So we see this spike, models are going to think that COVID is going to be trending upwards. But in fact, this spike isn't real. It's just due to a reporting artifact. How can we deal with that? Well, one way to deal with that is to look at what auxiliary signals say about the same county at the same point in time. And here are 4 such auxiliary signals. One is antigen test positivity rate. This comes from medical devices that Quidel produces. Quidel is a partner of Delphi. We make this data publicly available. They're the largest antigen test manufacturer at this point in the US for COVID, and I think also for flu. Okay, and that's in red. So you can see that this is actually trending down in late July. Okay. There's also Google searches. So this is I think it's in green, although my screen is a little bright. These are search queries on Google that relate to loss of smell and loss of taste, which were kind of highly specific to COVID in terms of there's not very many other reasons people will be searching for that combination. Okay, that's in green. Okay, it's actually quite stable itself. This is the fraction of people in that county that were attending outpatient centers like doctor's offices with COVID-like illness. That's in blue. It's computed for medical insurance claims. Okay, you can see that's very clearly trending down. And this is these are self-reported symptoms that come from SLDS, the COVID trends and impact survey that we ran. That's in purple. Also kind of stabilizing or trending down. Right, so all the auxiliary signals tell you that there's probably not a COVID surge, a surge of new infections, right? And so either informally, like triangulating situational awareness based on this, or formally building this into a nowcasting or forecasting model, these signals present tremendous value. The next opportunity is, this comes to the standardization aspect I mentioned. In order to produce the plots on the previous page, this is the code you need in R. So you'd load the COVIDcast package, and then you'd call this COVIDcast signal function, and it takes two mandatory arguments and then a bunch of optional arguments. The mandatory arguments are, what data source do you want? And the second argument is, what signal do you want from that data source? So, from the JHU CSSC repository, we want confirmed 7-day incidence of COVID. From the Facebook survey that we're running, this is SLDS, we want, this particular signal, which there's many, many signals. This one has to do with COVID-like illness that's being reported, self-reported. This next signal comes from the doctor's visits data source, and we want this particular smooth weekend adjusted, because weekends mess with medical insurance claims, COVID-like illness, and so on and so forth. So the point is that all of these function calls, there's kind of a unified way of making them, and there's a unified output for them. And so all you have to do is look at the API to figure out what you want, and data comes back in a standardized format. And plots like these in the previous slide, can then happen with a single call to for example, ggplot, or analysis downstream is immediate. We don't have to do all sorts of data wrangling in order to get these things in memory in a coherent format. Okay, so now let me move on to some challenges. Here's the first challenge, which is to deal with the revision patterns present in epidemic signals. So not all epidemic signals, but many epidemic signals are subject to revision, and they happen for different reasons. One of the biggest culprits of this are signals based on medical insurance claims. So this is extremely important data source, but it's also one of the most problematic in terms of revisions. And the reason is that medical insurance claims either get submitted or processed late. So if you saw the doctor today, your doctor might submit the claim to the insurer the same day, the next day, 5 days later, and the insurance might process it in a matter of days or weeks, or many, many weeks. There's some kind of stochastic process by which these things get completed. And so if we ask the question, how many people attended the doctor in your county on a given day that presented COVID-like illness, and we're computing that based on medical insurance claims, the answer will change depending on when you look back. So here's an example of that being played out in California in summer of 2020. So we're asking what fraction of doctor's visits were due to COVID-like illness in California in late August. Okay, and if we were to ask that question on September 1st, and we make an API call on September 1st, here's what we would have gotten. We would have gotten this red curve. Okay, this is the fraction of patients each day attending the doctor with COVID-like illness. If we were to ask that same question a week later, then we would actually have gotten this green curve. It's the same reference date. We're still asking about late August of 2020, but we're just asking the question at a different point in time. And so now there's actually more claims available in order to compute this signal, and so you can see it changes. If we ask it 2 weeks later, we get this blue curve, and we ask it 3 weeks later, it gets this black curve. So fortunately, we can kind of see it stabilizing. That's obviously good. We don't want to see the variance increasing. It seems to be decreasing, which is what we want to see. But there's clearly a big revision pattern here that we have to deal with. And this is important for to understand for any kind of real-time endeavor. And we call this backfill. This is the behavior that causes signals to jump based on, revisions. Fortunately, with medical insurance claims and with other signals as well, backfill tends to be fairly stochastically regular, which means that we can use statistical models to predict finalized signal values from, provisional data, just based on the history of revision patterns for that signal, let's say in that location. And these models that we fit are fairly simple. They're just regression models. They're like auto-regression models. So they're very simple time series models that predict finalized values from provisional values. And here's a concrete sense of how well they do for medical insurance claims. This is a plot that has to do with, actually, I think it's just exactly with this COVID-like illness signal in doctor's visits, but it's averaged over many, locations and many points in time. So on the right, on the x-axis is lag. It's how many days are you looking back in order to ask a question about a signal value. So, for example, we're asking, what does COVID-like illness look like 2 days ago if lag is 2, or 2 weeks ago if lag is 14? And this gray dotted line is the fraction of claims that are available of the total number that will be available eventually, okay, after that many days lag. So after 2 days lag, you only see about 15% of the total volume of claims that you'll eventually see. So 85% of the data is missing. Okay, and after 14 days, there's about 65% of the data available. So you can see that it gets backfilled very slowly. And in red is the relative error, just measuring the relative error of the provisional signal value at that lag with the finalized signal value that would be available many, many, months later. Okay, so we can see that after 2 days, for example, there's about an 80% relative error. So the signal is going to jump a ton from that point on. And even after, 2 weeks, there's still about a 20% relative error, which is very, very significant in terms of the variance that's present. This blue it comes from a simple regression model. Okay, this is the relative error obtained by a backfill projection model that's trained on the history of revision patterns for this signal and whatever location we're looking to perform this kind of imputation on. And so you can see that after 2 days, we're already down from 80% relative error to about 15% relative error. So it's a huge improvement. And if you remember how much is missing, that's about 85% of the data missing. You only have a 15% relative error. So this is not a bragging point of our models. I think the models are very simple. It's really speaking to the fact that this kind of modeling is possible because the revision pattern is regular. And this kind of thing isn't done enough. It's basically ignored in public health. And in public health, the thing to do would just be traditionally to not publish the signal until the relative error is low enough, which introduces like a huge latency. That's the current practice. Don't publish the signal until 2 weeks later, let's say, because then at that point, the relative error will be down to 20%, which may be acceptable. But we can cut down that latency tremendously just by using statistical models. Okay, another challenge is to deal with geographic incompatibility in signals. And let me stick with the medical insurance claims example, because I think it's very important. In medical insurance claims, we receive data from, let's say, a particular insurer for a particular data source. And that insurer may have different market share in different parts of the country. So in one part of the country, it may have, let's say, more pediatric hospitals that are part of its market share. Another part of the country, it may have more geriatric hospitals that are part of its market share. And in a third part of the country, it may have a different market, different kind of mix of hospital types entirely. And then what happens is if you compute the fraction of outpatient visits with COVID-like illness in each of these locations, you get this kind of bias that doesn't allow you to compare these numbers across locations, right? Because you're reflecting different populations essentially. And for privacy reasons, we don't know the market share. We can't actually get access to that. So it introduces this bias in signals that is very hard to reconcile. And the only thing that you can really say is how much has COVID-like illness in a given location changed from where it was in that same location, many days ago or yesterday or whatever some temporal comparison would yield. You can't really compare it across locations very easily. And I won't go into details here. This is just showing you 2 ways of computing correlations, one sliced by time, one sliced by space. And you can, basically the point is that you can see for some signals, they have great time-wise correlation and great geo-wise correlation. But for other signals, they have great time-wise correlation, but very poor geo-wise correlation. And that's because of this geographic bias issue. And I would say that dealing with that is at present an open problem. It's a very significant challenge that we're facing, not just with medical insurance claims, with other signals for other reasons. And I'd say I just wanted to introduce that as a big challenge. Okay, I think I'm going to probably skip this very quickly because I have two other examples I want to get to that I think are probably more exciting. But this was something that we've been doing for flu for many years. We had operational nowcasting models for flu. So basically, the idea that I'm trying to convey here is that just like there's backfill in medical insurance claims signals, there's also backfill in public health reports. So if you're looking at public health reports for flu, then you would also like to be able to, reconstruct what we think the finalized signal values will be from provisional data. We call that nowcasting. That's another word for this backfill projection. The nowcasting model we built for flu actually used more than just historical revision patterns. They used other data as well. And there's kind of a fusion common filter type model that we use for this, that we've been using for many years. And that's being shown here. The real-time nowcasts overlaid on top of finalized values. So you can see that over 7 flu seasons, at least nationally, it was quite accurate. Now I'm going to move into an even harder nowcasting problem for COVID. And this is actually the subject of the paper that I mentioned that we wrote for the statistical science issue. And that's to do both real-time backfill projection and real-time deconvolution. So for COVID, we had a kind of reporting pipeline that dropped cases aligned by when they were reported, not aligned by when the tests were run. So at any one point in time, if you ask what's the number of case reports today, that only reflects when those case reports were made to the, let's say, to the CDC or to the governing health agency in whatever location you're looking at. It doesn't reflect when the tests were run or when the infections began. And so this was a project that I carried out with a student and another Delphi member, which is to try to, in real time, deconvolve these case reports back into an estimated time series of infections that are aligned by symptom onset. And there's 2 aspects that make this challenging. One is backfill, the fact that you get revisions to data over time. And the second is that we're doing real-time deconvolution. It's not just like we're trying to predict the value of some measurable, observable signal. We're trying to predict the value of something that's actually latent, that's only relates to what we observe by a convolution. And so this is the convolutional distribution that we estimate that relates, for example, symptom onset to case report. So, if your symptoms onset today, then what's the probability that your test will actually be reported today? It's not 0 at this point in time. It's, if you manage to get a test that same day and that test managed to get reported that same day, that would mean the case report coincides with the symptom onset. And this is the probability we estimate of that happening based on other data that comes from basically line lists. But you can see there's a very big right tail. So even, this is like 45 days later, there's some non-trivial probability of seeing the case being reported after the symptom onset. And so what we do is we try to take these gray dots, which are case reports that are available, and we try to deconvolve them but with this estimated symptom to report distribution in order to get an estimated time series of symptom onset, cases by symptom onset. And that's what is in, that's what's in red here. Okay, this is red dotted line. And you can see the deconvolution is very problematic around the right end of the plot because there's very little information you have here to do deconvolution. And this black curve is kind of this, is what we consider a gold standard estimate of cases aligned by symptom onset that we're able to compute like a year later, basically, with complete data a year later. So it's not available in real time. What we see from using things like backfill projection to account for revision patterns and also fusing in other sources of information than cases that come from auxiliary signals, we're able to estimate in real time for the most problematic period, which is the last like 10 days, what's shown in these green triangles. So you can see that it's much more accurate and much closer to the kind of ground truth gold standard that we would have computed a year later. Okay, and let me go through this example and one more example, and then I think I'm going to quit and take questions. So this is just a follow-up on the last plot. What we get from this is something that I think is quite promising, which is an actual leading indicator of hospitalizations. So let me first tell you why cases don't lead hospitalizations. So the case reporting pipelines and the hospital reporting pipelines in the US are not the same. They're actually completely different. Hospitals get reported to the HHS directly. From hospitals report to the HHS directly. So, we have something like 5,500 hospitals in the US. They report to the HHS directly. There's about a 1-day latency for the most part in hospital admission reports. Okay, so they're actually pretty close to real time. They're very burdensome for hospitals. Case reports do not operate that way. Case reports get reported to the county, which get reported to the state, which gets reported to the CDC through a different mechanism. And that mechanism, there's a lot of latency in there, and cases could be reported, as I mentioned already, anywhere between 1 and 40 days after symptoms would onset, for example. And what you end up seeing, because cases are much more delayed than hospitalizations, that if you were to take the correlation of cases and hospitalizations in a given location, and you were to look at lags of correlations and hospitalizations in that same location, and take the lag correlation between, let's say, cases 5 days ago and hospitalizations today, then you would see that actually the maximum correlation is obtained at lag 0 when cases are measured contemporaneously with hospitalizations, which is not at all intuitive. Of course, this is not what we kind of expect is happening in the actual phenomenon, right? We expect that cases precede hospitalizations. But because of the massive delay relative in cases relative to hospitalizations, they're basically contemporaneous. Right, so this is the lag correlation, and it's maximized at lag 0. What we see instead, if we look at these estimated infections that come from real time, these are real-time estimated infections that I showed you on the previous plot. So that would be this, basically these green dots going back in time. We see that the correlation is actually maximized at lag 11. So these estimated infections, are maximally correlated with hospitalizations 11 days later, which is much more intuitive and obviously good. It gives us a leading indicator of hospitalizations. And the correlation we obtain at lag 11 is not what we would have obtained with cases until something like a week later. Okay, so there is information here above and beyond whatever the case reports present at that point in time. And my very last example of an opportunity that I want to describe is another nowcasting problem, but this one is set up a bit differently, and it's also something that I'm quite excited about that I'm working on with students right now. And it's a hypothetical situation where we say, what if hospitals only reported to the federal government once per month? Not every day, but once per month. Okay, what if every month hospitals dumped the reports from the last month on the federal government, and they didn't report for the next 30 days or 29 days at all? And in that hypothetical situation, we ask, can we take auxiliary signals? So for example, hospitalizations as measured through medical insurance claims, in order to nowcast hospitalizations that would be reported in the interim period to the government. Okay, so that's the hypothetical. And this plot is showing every green dotted line is the reporting date in this hypothetical. So at every green dotted line, you get hospitalizations for the previous month. So for the segment between that dotted line and the last one. And what are being shown are the actual hospital reports in pink, and the hospital reports that we would have estimated using a model that only uses medical insurance claims. So this model is actually, it is fit faithfully in the sense that at any point in time, it is only fit using data from the past. So it uses the relationship that it has seen between medical insurance claims and hospitalizations to the left of this green line in order to estimate what happens in the segment to the right. This is not retrospective. It's done using, like I said, data in the past. And what's most exciting about this is that the dynamics are completely nailed by this model. So it can be off by, more or less in terms of absolute error at various points in time, but the dynamics are correct, which means that when hospitalizations are surging, when they're increasing, and you only, let's say at this point in time, you just got hospitalizations prior to this green dotted line. They end up surging over the next month. Your model will tell you that that's going to happen just by looking at medical insurance claims, right? The purple line is increasing. So the nowcast that you'd make would be increasing. You'd be realizing that something's going on in hospitals. Okay, then you might actually even in real life, you might want to actually increase the frequency of reporting at that point, once every 2 weeks. Okay, once hospitalizations start decreasing, the model also gets the dynamics right. Then the nowcast would tell you that they're decreasing. So maybe in real life, you'd actually probably then decrease the reporting frequency at that point from 2 weeks back to a month. Okay, I think this is a very promising way to try to reduce the reporting burden in public health with these kind of nowcasting models. Okay, so that's it. That's all I have. Thank you for letting me go over time. I'm sorry that I dropped out in the middle there. Looking ahead, the term vision of the is to make epidemic tracking and forecasting as universally accepted and useful as weather forecasting is today. I think it's ambitious. I don't think that we're certainly not going to achieve it by ourselves. There's a community of people working on this. It still is very ambitious, but I do think that it is possible. And the thing I want to really by saying is that we believe in open science. We welcome any and all contributors. If you look at this last slide, there's actually members of Delphi that are spread across many different institutions. We welcome anybody who wants to contribute. It's all kind of open source, open science. And I'd like to thank especially the whole Delphi team. I am just the kind of messenger for a lot of this work. There's a ton of people that were involved in putting this together. And if you click on this link, you'll see their faces. Of course, they are owed many thanks for a lot of this work. Okay, thank you very much for your time.
Thank you so much, Ryan, and thank you, everyone. So let's move to the Q&A session.